Welcome to the Consulting Specifying Engineer webcast. It's about time, why time accuracy and resolution matter in critical power management system design, sponsored by Schneider Electric. I'm your moderator, Amara Razgis, and I'm happy to join you today on behalf of Consulting Specifying Engineer and CFE Media. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your own computer or by adjusting the volume on the webcast platform. If you are having trouble or technical problems with the audio or the slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. Type questions for our speaker in the Ask a Question box on the left side of your screen. The live Q&A session will begin once his presentation concludes. Today's webcast is being recorded, and you'll receive an email within a week with a link to the on-demand event. To download a certificate of completion and a PDF of this presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the archived version of this webcast. All right, well, I'm happy to introduce today's presenter, Ram Kaushik. Ram has 25 years of experience in technical and business roles in engineering, IT, and software development. Ram is U.S. Offer Manager at Schneider Electric's Digital Power Division and manages strategic marketing direction for energy and power reliability management offers within Schneider Electric's EcoStruxure Power software suite. He manages a portfolio of hardware, software, and services targeted toward industrial and commercial facilities, data centers, and healthcare buildings. He presents frequently at seminars, industry forums, and at technology panels. Ram began his career as an automation applications engineer at American Electric Power. After that, he worked in industrial automation and power system application at Square D before venturing into a software consulting career at a series of technology companies and startups. He's worked as an offer manager for Schneider Electric since 2012. He holds an MBA from Vanderbilt University and a master's in electrical engineering from Rensselaer Polytechnic Institute. Thanks for joining us today, Ram. Let's get started.
Thank you, Amara. It's my pleasure today to present on what I think is a very underrepresented topic. It's about time. It's the most underutilized, I would say, a resource which we find ridiculously underrepresented in our personal lives, and design and specification in critical power systems. It's exactly the same, right? Time is often an afterthought. So I hope to correct that impression today. So the learning objectives would be to give you a sort of a way to think about time accuracy and resolution as it pertains to different energy and power related applications. There are several standards which are applicable here, and I hope what you learn today will help sort of future-proof some designs that you work with clients on an everyday basis. Okay, so let's dive straight in. So the agenda today is the flow of this presentation is I want to first introduce you to this concept of time accuracy and hopefully convince you about why you should even care. I also want to run through some standards and time sources. This is a very deep topic, so what I will probably cover is I will skim the surface, but hopefully give you enough enough to delve in deeper if you need to. The third topic I think is the most interesting in my mind is how time accuracy really impacts specific applications and what are the consequences of not getting it right. Finally, we'll try to summarize the highlights of the presentation, and as Amara pointed out, we will have a Q&A session at the end. Okay, let's jump right in. Let me introduce the concepts first of time, synchronization, and accuracy. Why are we even talking about this topic? Without time accuracy, in critical power systems and critical facility management system, there's really no context or perspective to this huge amounts of data that we are collecting today. I don't know if Confucius really said this, but he should have if he didn't. Man with two watches is really never sure what time anything happened. And the goal of this presentation is not necessarily over-engineer something, but just to put time accuracy and resolution front and center when we think about specific applications. I will use electrical systems in my examples, but the same principles you can extend to mechanical, safety, and other facility systems. Okay, so let's introduce some of the terminology and jargon. Some of it is obvious, but I see a lot of terms being used interchangeably, and they sometimes mean different things when you're actually trying to design a system. So this is the terminology I will use in this presentation. So let's start with resolution. This one's easy. So it refers to the precision. So obviously milliseconds is more precise than, say, hours or minutes. So you could have high time resolution and still have poor accuracy. So the second term is referring to the amount of error in the measurement. The third is sort of the, I will introduce this topic in some length in future slide, but it is the sort of frame of reference that you think about when you're thinking of a particular application. Like I said, we'll get deeper into this. Time criticality is sort of an inferred idea, and it comes from resolution, accuracy, and horizon. And finally, time synchronization, which is really coordinating these independent clocks on devices with a time reference. Okay, so let me try to convince you with two examples on why both resolution and accuracy can be important. Consider the first example. This is a sequence of operations report following a critical power event. Could have been an outage. In this case, it was a process trip. So I'm going to point out two qualities, two attributes in this screenshot. So remember that after a power system event, it is often a crime scene investigation situation where you're trying to determine the murderer. And in power systems, milliseconds matter. You have breakers that operate in 3 to 5 power system cycles, and 20 milliseconds could mean the difference between a breaker that should have operated or a relay that should have detected a fault. So milliseconds matter. If you look at the highlighted section, the resolution is nowhere near enough, right? Even if the time was accurate, the resolution is not. In the second highlighted section, the resolution is fine, but the accuracy is not. This clock has not been synchronized to the proper year, and you can probably make a good guess that it is, but imagine several devices which are not synced accurately, right? So there is not enough time accuracy to determine if this line was actually dropped because of this event or not. Second example, consider a production efficiency chart for, say, a food and beverage plant. The objective is to look at energy usage intensity, which is look at energy with the context of production. right? So you could have two different processes. In this case, it's two different mixers for different size beverage bottles. And the orange line you see is the overlaid production values. So it looks like this is useful data. There's only one problem. One of these processes is in China. So when you line up this data, there's a small matter of a 14-hour time difference in time zones. So when you aggregate this and you have not synchronized time correctly, you could get completely the wrong results and actually penalize based on incorrect KPIs. Okay, so what does that mean? So we talked about resolution and accuracy. In general, I would say resolution and accuracy needs will correlate, right? When you talk of an application where you really need, say, resolution of minutes or months or whatever the value, the accuracy will also fall in the same region, right? So for a time horizon of interest, what do I mean by that? If you are dealing with power event analysis, you are sort of thinking with a frame of reference of milliseconds. If you're doing energy usage analysis, operators think in months. They analyze months of data. So that is a frame of reference which dictates the aggregation or roll-up interval. Okay, let's unpack that idea a little more. So here are some typical applications, and some of it is intuitive, right? So when you think of developing an energy model for a facility where you want to predict what the energy usage in 2020 is going to be, you will probably use data which is for the past 2 years. So you're sort of thinking in terms of years. On the other end of the spectrum, power event analysis, where you're analyzing breakers, power disturbances, power quality, you are thinking in terms of milliseconds. So that's sort of an intuitive time horizon matrix. And once that is clear, the next thing that pops up is, okay, time criticality of, let's say your resolution is off by 3 seconds. As long as your data is in years, it probably doesn't matter. So I would say these applications fall in the low time criticality time horizon. And I would classify, say, capacity management or peak demand response, where you are trying to respond to utility incentive program where you are curbing demand in return for some monetary incentives. You probably have a few minutes to react, right? So you're dealing in minutes. And like I said, at the other end of the spectrum, it's really high time criticality, where you really need data to be accurate to milliseconds. Okay, so we've sort of unpacked a few terms here. We talked about resolution, accuracy, a time horizon matrix, and then time criticality. So these are related concepts, but I wanted to systematically step you through why certain applications need certain time criticality. So time horizon will really determine the time criticality for these applications. So here's the path we took. So if you're thinking in terms of, say, minutes, that will determine a time criticality which is, say, medium, where your resolution can be in seconds, or if you can get better, fine, but you shouldn't be significantly worse. And that determines what your time synchronization for the devices that are actually collecting this data. How accurate do the data logs and the event logs on those devices, how accurate do they need to be? So this is sort of the flow of thinking. So what that does is, so if you look at this table, it's a list of what I would call a menu of applications that we run into often in critical power facilities. right? And you can probably dream up equivalent ones. And I'm sure, we have experienced consulting engineers in the audience, and they can have other applications that they work with their customers. All of them you can classify with some rough, low, medium, high impact in terms of time criticality. And that comes with that comes a recommended accuracy, right? So you have a minimum accuracy and probably what you might have to live with depending upon the devices that are collecting the data. But if you have influence on specification and design in, say, a greenfield project, you really should be thinking in terms of these accuracies. And we'll get into some of these applications. I have 3 examples of applications where hopefully I will prove that you really need this kind of accuracy. Okay, so with that background, let's take a short tour through the time accuracy sources and standards. Like I said, this is a complex topic, so hopefully I'll just hit the highlights here. So broadly speaking, time accuracy standards can be divided into Ethernet-based time protocols and serial time protocols. Within the Ethernet-based time protocols, network time protocol is an example where a master can send out a time signal and the slave devices over Ethernet can synchronize to that time. Simple network time protocol, and we'll get into details in a minute. I wanted to give you a broad stroke first. So Ethernet-based protocols over Modbus from any kind of management software that you have. And finally, precision time protocol, which is defined in an IEEE 1588 standard. And we'll get into that as well. So that's sort of the first broad category. The second category are the serial time protocols. And IRIG-B and DCF77 are 2 popular ones. 1/10 is a less popular one. Doesn't have a whole lot of support, but it's still around. So that's sort of the serial time protocols. Now, I want to also make the point that the idea of relative time and absolute time matters. So what that means is that you may be able to synchronize all the devices within a facility and still not be accurate when you compare with another site, right? And traditionally what has been used to solve this problem is a GPS receiver, which actually syncs to a satellite. And the technology has actually come down in price enormously, right? So I will again show you more details of this approach. So Ethernet-based time protocols and serial. Okay, in terms of history in the industry, I would say, in the 1990s, we were in the simple but not accurate era where the power management systems would report historical data to the nearest second. We would use maybe Modbus or NTP to time sync. In the next era, we had sort of the serial IRIG-B or DCF77, which is accurate, but again, I will show you some disadvantages with this method. They're not necessarily simple or easy to design. Today, I think we are at a point where the new IEEE 1588 standard is stable enough where we can actually get simple and accurate. So again, I'll show you more details about this. Okay, let's do a quick comparison of time synchronization technologies. They can be divided into this time criticality lens, right? So you can look at this accuracy as high, medium, or low. Keep in mind that it's not necessary that supposedly a more advanced protocol media like Ethernet gets you higher accuracy, right? So for example, SNTP is an Ethernet-based time synchronization technology, but it only syncs to the nearest second. Whereas you have a serial, say like an IRIG-B protocol, a serial protocol media gets you to within a millisecond. And I've taken a crack at what the relative cost will be, and this is based on our experience in several projects. You will see that the PTP standard is marked as kind of $2, but it is coming down fast in price. So this is debatable whether it's it's really adding a whole lot of extra project cost. Okay, so let's move on to a slightly different topic, but related. Let's take a look at how devices really handle this time synchronization. So if you take devices which are sort of low time criticality time horizon, right? Many of them record time-stamped data. Without any kind of synchronization, they will drift, clocks will skew, and you will, when you're trying to collect data, you will find data like 1901-01, right? We see that a lot, where these devices have just reset at some point and it's sitting around without a synchronized time. So it's really recommended that you sync it, even if it's low time criticality. We find, we use some technology to really synchronize the clock. Data from devices without any inherent sync capability, you can still timestamp. You can hardwire any kind of discrete circuit breaker status, those kinds of I/O into an externally time synchronized device, right? So there are other devices which have I/O capabilities, like a sequence of event recorder card, where you can hardwire this kind of discrete I/O and it is still down to the millisecond accuracy. You can also use timestamping using on-premise management software, which is subject to some inaccuracies because it really depends on how network latency, right? So if you have hundreds of devices connected, the sync happens when it happens, right? So it's not going to be as accurate as you would like for that particular application. Medium to sort of high time criticality devices, I have some examples of power quality meters or very accurate sequence event recorders. They can achieve 1 millisecond timestamp. They have provisions to synchronize to an external time reference, which I'm going to talk to in a few slides. Devices that fit in this category are power quality capable meters, some relays, and some specialized I/O modules. So that sort of fits in this critical power space. So that's a little detour on how devices actually handle a time synchronization capability. Too many slides. Okay, there we go. Okay, what do I mean by accurate time sources? So typically a time sync master will receive timing information from a GPS satellite with an antenna, which looks about like this R2D2 picture over here. The master will then generate pulses containing time data over a network. And like I said, this can be either serial or Ethernet. And the devices will decode the time information and set their own clocks so that the data that they record is accurate to that sync pulse. I made this point before that you can synchronize to relative time, but it will lead to inaccuracies when you're trying to overlay data from multiple substations or multiple sites. Let's look at the general disadvantages of serial time synchronization. So you can see that this picture has a lot of wiring. It basically needs an independent time synchronization network. There is some complexity that comes with this, and obviously increased cost of design implementation. It's still worth it for critical power applications. You don't have an alternative, right? And I'm going to show you some alternatives. as well. So these are sort of general disadvantages. I'm going to also show you some specific disadvantages of the synchronization standards we looked at earlier. So Ieee, which gets you 1 millisecond accuracy, has pretty good adoption, but it's distributed at 5 volts. So it has some interference issues, distance and device limitations. You might have to use repeaters, and you have to deal with the messiness of that. DCF77 also can get you pretty good accuracy. In practical terms, it's difficult. We found it difficult to achieve the theoretical published accuracy. Adoption is very mixed in terms of devices that support it. On the Ethernet standard side, the most common ones are SNTP and NTP, and Modbus, right? So these are fairly common Ethernet time sync standards. The pros are they're very simple, right? If you're connecting to Ethernet, you're probably going to get this. You're going to get some time synchronization accuracy. The cons are the biggest downside, in my opinion, is that it's really not sufficient for these high, what I call the time criticality equals high, right? In that spectrum of applications, this is not, some of these SNTP, NTP, Modbus are not accurate and down to the correct accuracy for those applications. Okay, if you look at the IEEE 1588 standard, which is PTP, Precision Time Protocol, the National Institute of the NIST site also maintains a good site for good area for PTP documentation. I would recommend taking a look there. The cons to this, until probably a few years ago, was it did require some extra hardware, and my next slide will show you what that is. The pros are it's extremely accurate, very straightforward to deploy, ensures accurate time sync for almost all the spectrum of applications, right, from time critical ones to non-time critical ones, right? So it's really future-proofing your design. So what's the catch, you will ask, right? The expense has really been the catch to date. So if you look at the typical architecture of PTP, there are 2 published profiles in the standard. One's called Power Profile and one's called the Simple Profile. The Power Profile will require these intermediate clocks, which add quite a lot of expense, right? However, if you set this up as a simple PTP profile, it removes all these intermediate devices, and really all you need is the clock and the antenna to synchronize these slave clocks over an already wired network. So the added expense is really not relevant in the context of your project. So today's technology, really prices have come down. The satellite clock plus antenna plus hardware is really pretty good. If you need even more accuracy to microseconds and stuff, you need the Power Profile. But I don't think, we have not encountered too many applications in real life where you need to go the whole hog on that. All right, so what are the time synchronization implications for specific applications, right? So I've told you that you need accurate time sync for certain applications, and other applications you may not need it as much, but I haven't proved that to you. So let's dive in. So this is the same time horizon matrix I showed you earlier, where I claimed, without evidence so far, right, that these applications could do with low time criticality. The ones on the left and the ones on the right are sort of in the high time criticality area. And things like demand management, backup power testing, those applications you could classify as medium time criticality. Okay, I've just said that. I've not necessarily proved it to you. So let's do that. So for this particular discussion, I'm going to select 3 applications, each of a different time criticality: low, medium, and high. So we'll select energy modeling on the left, electrical distribution monitoring in the middle, and power event analysis on the right. Okay, so let's look at each of these applications, and the framework that I'm going to use is the following. We'll look at a brief description of the application. I want to show you some consequences of getting it wrong, right? What are the consequences of bad resolution or accuracy? And what design considerations as consulting engineers or people who work with specifications, what are the things that you need to consider, and what implications it will have on specifications you write. So like I said, I'm going to pick these 3: energy modeling, electrical distribution monitoring, and then finally power event analysis. Okay, so let's dive in. The first one is energy modeling. Okay, what is it? Facilities often need to forecast energy for various things. One is they may use the model as a way to negotiate rates with a utility. They may use it to drive energy conservation measures. They may use it to meet energy program standards like ISO 50001 or get lead points, any number of reasons. So energy modeling is an application that many customers are beginning to use. Okay, so I have some examples here where we've developed a model and we are tracking actuals, and we look at the error, right? So we might want to see, okay, now the energy use is actuals are less than the model. So either we've discovered some magical source of renewable energy in the building or in the facility, or something is, there's a machine that failed, and because of the outage, we use less energy. Anyway, so that gives you a very broad sweep on what this application is. What are the consequences of getting it wrong, right? So misaligned data really leads to inaccurate models. So I gave you one example before with the production data. Let me give you another one. So let's say by misaligning data, and you have devices that are capturing energy data that are not synchronized, you're off one facility by a day, right? December 23rd and 24th are critical days in both energy usage and desperate last-minute Christmas shopping on Amazon, right? So an error there is going to skew your model a lot, right? So that's an example of how misaligned data really leads to inaccurate models. Lost time to data cleanup. You have operators or analysts trying to clean this data to really match the model. Garbage in, garbage out is very clear in the modeling world. You can develop a model for anything based on bad data. So I mentioned ISO 50001 compliance before. We see that in the industry quite a bit. Energy budgeting errors. So often, like chief sustainability officers or chief energy officers will use the output of energy models to budget energy costs for the year. You get it wrong, you might even be penalizing or rewarding departments based on incorrect KPIs, right? So energy models have consequences, and getting time wrong has impacts. Okay, so given the impacts, what are the design considerations? I'm not going to go through all of these in the interest of time, but let's take a couple of them, right? So preferably you need 1 year or maybe even more of energy data to derive a reliable model. Typically, a model needs independent variables and like things that drive energy use, like weather, production data, anything that impacts. So in a hospital, it could be occupancy. In a building context, it could be occupancy. Again, weather is a big factor. And those variables better be synchronized to the same resolution. So if your energy data is coming across as once in 15 minutes, and your production data is coming once a minute, that is not a recipe for success in a model, right? You will develop some model, but it's not going to be great. So at the very minimum, devices should be time synchronized to at least in this low time criticality time horizon. There could be other factors, like you could be developing an energy model with a dollar figure. In that case, you might want to synchronize with a utility demand pulse. You might need revenue meters. In some cases, multi-tariff. Like I said, I'm not going to go into all the details here, but just some design considerations to think about for this application and how time matters, right? In terms of specification implications of this time attribute, so if you have non-network meters disconnected from energy management software and you're manually reading meters, right, this is, again, a recipe for trouble. At least let's specify networked intelligent devices with time synchronization of some kind. At least NTP is what I wrote here. If we can do better, we should. Choice of the correct meters at the correct location is big. And the software should have kind of data aggregation and disaggregation. So if you're gathering data in months and years and seconds, your software should be able to have the roll-ups and slicing and disaggregation features to unbind that in that time frame that you're working with. Okay. That was application one. Like I said, I'm going to run through 3 applications here. The second one is electrical distribution monitoring and alarming. So let's take a quick look at that. What is it? It's pretty self-intuitive. It helps operators run the power systems at their critical facility, respond to events. So typically a system might have real-time operator screens, trending, alarm annunciation, things like that. What are the consequences of getting it wrong? Inadequate operator response. So if you look at this picture on the top, it has a timestamp and when certain events happened, maybe a switching event. If you get it wrong, alarm sequences are messed up and just creates operator confusion. It could have impact to safety procedures. Arc flash risk is one. You could be exposed to live equipment because you think something happened at a time that's different from reality. And related applications like demand management are also affected by poor time accuracy. So you might be thinking of setting a new peak demand, which now takes effect for the rest of the year, and you're shelling out to utility because of that. So these are some of the consequences. Let's follow the same design pattern here. So design considerations, the time horizon you're thinking about for electrical distribution monitoring is really seconds. You can react in seconds. Operators can react in seconds. So the resolution or accuracy of alarms and events should really be in this, at least in this time 10 to 100 milliseconds, which I'm calling medium. So the choice of meters or choice of any other intelligent devices which have onboard data should be time-stamped with the proper time sync architecture. So I suggested PTP before. IRIG-B is a possibility. You could probably get by with NTP if you're probably in the seconds. It may not work as well. It's always a trade-off, right? It's always a design trade-off. Critical I/O, I would recommend it's connected to devices with really good timestamp and time sync capabilities. And again, there's software implications to this. Specification-wise, similar implications. I would say I would add like point list with associated time accuracy listed for each point. This is a good practice. specifying the exact time accuracy of your displayed data. What do you want to happen with what accuracy, right? Specifying that ahead of time is going to save a lot of time and aggravation. Okay, application number 3 is power event analysis. What is it? Well, this is the CSI that I talked to you about before. It's really root cause analysis to assess what happened, when, and tools that are used might be sequence events reports, some kind of time analysis tools. You could be looking at electrical parameters during an event. So all these, there's many tools in the toolbox to do this. What are the consequences of poor time accuracy here? Well, just lost time in root cause analysis. You're chasing timestamps, you're piecing together evidence, and you're playing guessing games, right, on sequence of misoperating equipment. I have some examples here, and this is all very, very real experiences, right? Did the transfer switch operate? You don't want to be the Amazon operator when a data center dropped and the CEO is trying to figure out who to blame, right? And you're opening up event reports with incorrect time, right? So these are operator consequences. Obviously, they have impacts on how you design systems. So impact on uptime, record keeping. If you have insurance, we see that sometimes where you have to have an incident report which is accurate for all of this kind of stuff. Fundamentally, it's really the worst impact at the worst possible time, right? It's a crisis, and you're trying to piece information together. I would say from a design perspective, it's either a time synchronization, or a time sink, S-I-N-K, right? You're syncing time when you can least afford it. Okay, so what are the design implications? Resolution and accuracy really has to be in the, I would say, 1 to 10 millisecond region. You're in the high time criticality. Your choice of data recorders, power quality meters at critical locations is going to matter. Time sync architecture, PTP, IRIG-B, you cannot make do with NTP or Modbus, right? You're in seconds there. It is not going to work. Critical I/O, again, needs to be time-stamped to this millisecond area, and again, everything has software impacts. You should have timeline analysis, event reporting, those kinds of capabilities. Spec considerations, like I said, IRIG-B or PTP, specify appropriate power meters or power quality meters or any kind of data recorders with with this associated time synchronization. Again, your point list can be useful as well with associated time accuracy. Okay, very good. So that was a whirlwind tour. So let me try to at least recap some of the design principles we covered today. We looked at time horizon, or a frame of time that you need when analyzing different applications. We looked at what that time horizon really means in terms of impact to design and specification. I would say still, no one size really fits all, right? It's always a design trade-off. Time resolution and accuracy has to be appropriate for the targeted application. We don't need to over-engineer applications where you don't need that time resolution. So for energy, if you're only interested in energy modeling, for example, in the example I showed, it is okay to be off by a second, right? It's fine. But if the same device is recording power event data, it's not a good idea, right? So applications matter, and that's what drives time resolution and accuracy. We didn't talk that much about this, but different vendors really support different time synchronization protocols. So the standards are beginning to have an impact. So PTP is becoming more widely prevalent. I would say let's looking at time synchronization architectures during early design phase is a good idea. Segmenting your network into time criticality zones. So I've seen this done very effectively, where you actually look at the facility design and you say which pieces you really need data which is very time critical, and where can you make do with, at branch level, you're only collecting energy data, you can make do without maybe running a PTP signal there. But you might get it for free, right? That's the other thing you have to keep your eye on. If you network that device and it's capable of that synchronization, take it. So specify products with time synchronization in mind. I think what happens is this is often an afterthought, and that's when it gets expensive. So at design phase, if this is planned and it's engineered for, it does not add that much cost. But retrofitting some of the stuff can get messy, and operators and your customers have to live with the consequences of this design during the lifetime of that facility. Okay, I also had some additional resources here. There's a couple of videos and a specification that you can look at, Division 26. We have some consulting engineer resources. I would recommend looking at the Digital Applications Design Guide, because it talks to some of these applications we defined, and it gives you a sense of what you can accomplish with those applications. I was hoping to have the tech guide that we are working on for this exact topic, time synchronization. Unfortunately, it wasn't ready for publication in time for this webinar, so I'm going to have to say coming soon. But please look for that. I'm sure we'll send it out through our marketing channels as well. And finally, there's a nice white paper by one of the pioneers in this field, Cyber Sciences, who designs high sequence events cards. Take a look at that white paper as well. And I think that kind of completes my presentation. Hopefully, it was valuable. I want to really thank CFE Media and CSE Magazine. They're really a great resource for our industry. I'm not saying that as a vendor, but as a tech buff and just as a consumer of information. So thank you all for attending and taking time out from your busy schedules. Hopefully it was valuable. I think we have some time for Q&A. Can I turn it over to you, Amara?
Yeah, thanks, Ram. That was absolutely terrific. I appreciate it. Now Ram will answer questions. Please type your questions for Ram Kaushik in the presenter area, or in the ask a question area on your screen, and we'll get to as many questions as time allows. Questions that we don't get to today will be posted online at www.csemag.com with the archived version of this webcast. And please remember to download a certificate of completion or a copy of the presentation. Use the Event Resources tab on the left side of your screen. Ram had several recommendations for additional reading, and when you download that PDF, you'll be able to link directly to those additional resources. All right, Ram, let's get started with these questions.
Yeah, absolutely.
All right. The first one is, for time-critical power applications, does iRig-B time synchronization still have a place in the industry? Can you talk a little bit about that, please?
Yeah, sure, Amara. That's a good question. So I touted the benefits of PTP. So I think that's a valid question when somebody asks, okay, iRig-B has been around for a while. It does do satellite-based time synchronization. Is it still valid? I would say that's an evolving story, right? PTP is becoming prevalent, more economically feasible. Like I said, satellite clocks have become, very cheap and very easy to install. So if I had a choice, I would say PTP first, but If the devices support IRIG-B and don't support the later protocol, then IRIG-B is a good choice for accuracy, but you still have to deal with the extra wiring and the hassle of running that wiring. So I think it still has a place in, especially when you're retrofitting with existing devices. But I'm tending to recommend PTP more and more.
Okay, excellent. Our next question, once I have all of my time data available from my power metering devices, what system do I use to archive the system for record keeping and future analysis?
Okay, excellent. So I'm going to attempt not to sell you Schneider software, but so there's many systems that allow you to sort of have a historian functionality, right? It serves as a database for energy and power management data. It allows you to slice and dice, aggregate, disaggregate, report on. Modeling is another feature that I showed you. You can use that data to develop energy models. So the software tool set today is enormous. And there are other vendors in this game as well. Schneider is obviously in this business, but there's many power and energy management software tools which allow you to save this data and do something meaningful with it, in terms of even energy, power quality, and general operating data, right? So there's many software tools available today.
All right, thanks, Ron. Very good. The next question, if PTP is distributed to devices like protective relays via a network cable, can the same Ethernet port and cable be used for data communication, or is it dedicated strictly to the PTP time signal?
Excellent question. I should have clarified. So you can absolutely use the same network. You can absolutely use the same data network to distribute the PTP signal. So this is actually one of the major advantages, because you in an IRIG architected system, for example, you're running an independent time synchronization network. With the Ethernet-based networks like NTP or PTP, you don't need that extra network cable. And with PTP, you get the accuracy. So yes, thank you for the question. I'm sorry I didn't clarify it earlier. Hope that's clear.
Yes, thank you. Got it. All right, and the next question is actually a multi-part question, Ram. So if you need me to repeat anything, just let me know. First, when was IEEE 1588 established? When was that standard established? Second, have vendors been quick to adopt it? And third, are there barriers to adoption?
Very good. So IEEE 1588, the first version has been around for a while, 2003, I believe. At that point, there were still some barriers to entry for vendors, because it had some, I would say, things which were not fully baked, right? So vendors took their own approaches, and it created some non-standard, I would say, different ways of implementing the same standard, I should say, which created some confusion. However, the standard was revised in 2010, I believe. I could be wrong on the year, but it was revised. And the subsequent standard has been pretty solid, right? So we've had more vendors jump on this bandwagon. You see more products that can actually sync to PTP. And in general, vendors have become better at synchronizing time, right? Even if you're not at PTP accuracy, for other applications, they are at least accepting other ways of time sync and generally paying attention to time, Mara. That would be my response, right? It was carelessly done before, but it's more relevant than ever today.
Okay, thank you, Ram. And we do have time for just one more question. In which of the power applications you mentioned, so in your examples, does accurate synchronization matter the most? Can you go back and describe that a little bit, please?
Yes, sure. I'm going to refrain from flipping slides here. But I'm assuming you can look at this in the in the recorded presentation. But in the time horizon matrix which I showed, I laid out different applications according to this time horizon matrix with low time criticality all the way to high. I would say on the high side, I would put I put power quality monitoring, which is it's looking at power disturbances, voltage sags, power events that really impact your facility, right? So power quality monitoring, you breakers, tripping, those kinds of things, you really need a very accurate timestamp. So that's on the high side. Power event analysis, where you're trying to piece together information based on an event that happened, also requires it's on the high side, right? And in the medium side, where if you can get better time accuracy, it really makes a lot of sense today, is things like electrical distribution monitoring, which I used as an example. Source control, right? When you have renewables in the mix, you have distributed energy resources, and you're switching on and off based on, you could be bringing in solar in case of an outage, or you're islanded from utility, you're bringing things back, and you're recording the time when these events happen. Those devices need to be at the high, high time criticality. So seconds matter to piece that information together.
All right, excellent. Thank you so very much, Ram. And thank you to the audience for the great questions. One more Absolutely. Thank you to our expert speaker, Ram Kaushik, for sharing his time and knowledge. And I'd also like to extend a special thank you to our sponsor, Schneider Electric, for sponsoring today's event. And now that we are just about done, we want to hear how we did. An exit survey will pop up on the screen as soon as this webcast ends. And please do take a moment to complete it, because we use this information to improve our webcast. Finally, on behalf of Consulting Specifying Engineer and CFE Media, I'd like to thank you for attending. This now concludes our webcast. Thank you and goodbye.
Thank you, Mara. It was a pleasure, and thank you to all of you.